All right. This one's going to be rough. All right, so I want to explain, mostly for myself, the part of the proof. This is a little too close to me. The part of the proof that shows what the variance of mu hat is, or the pseudo mean. So just as a reminder, the pseudo mean, mu hat, is a sample. It's a estimator. Call this the pseudo mean mu hat, or the sample mean, and it entails taking a sample of n points from the population, and then taking the mean of that. Taking the mean of that. Now, it is an unbiased estimator, meaning that the value of mu hat is equal in expectation to mu, or just the population mean. But we want to know what the variance is. So that's to say, suppose that we took a bunch of mu hats. So we took a sample over and over again. In the limit, suppose we took infinite samples of size n, and we took the mean for each one. This would give us a new distribution, which would be the distribution of the means of the samples from this population. And we know that the mean of those means, the mean of the sample means, would be equal to the population mean. But the question is, what is the variance? How spread out would the how spread out would the distribution of the mean of the sample means be? How spread out would the distribution of the sample means? Yeah. How spread out would the distribution of the sample means be? Would it be wide? Would it be fat? You would sort of expect that it would be smaller than the distribution of the population as a whole, because there's sort of more averaging going on there. So we're going to get closer to the we're going to get closer to the population mean. But what exactly is the variance? Well, so to figure this out, we want to unbiased estimator of the population mean. On average, the value of mu hat will be equal to the value of mu. All right, so to figure this out, we want to use the definition of variance. The definition of variance, sigma squared, is how we write variance, is equal to the expected value of xi of some data point minus mu squared. So we're squaring that whole thing. I should maybe write with different colors. I'm not sure what the color coding should be. So we're going to take this formula, but in this case, we're not looking for the variance of a sample. We're instead looking for sort of a variance of a meta sample, a sample of samples. And so that means that our xi, which again is just an arbitrary data point, in this case, our data point is going to be a sample mean. So that means that the sigma squared of the means of mu hat how it's spread out is the estimator mu hat is equal to the expected value of mu hat minus mu squared. Right, and so again, intuitively this makes sense. We're asking in expectation if we take mu hat, the value of mu hat, and this is in expectation. We take a random drawing of random sample. We take the mean of that sample. That mean is mu hat. How does that compare to the population mean? And then we square it because that's what we do in when we are trying to find the variance for reasons previously discussed. Excuse me. So this is our setup. And the thing that we want to do here is to start, we're just going to substitute in for mu hat, we're going to substitute in the value of mu hat, which we have defined. We've defined this is the definition of mu hat, is equal to the average of some set of data points. So mu hat is equal to 1 over n times the sum of xi, where I starts is equal to 1 and it goes to n. So that's just to say the average of some set of n data points minus mu squared. Whole thing is squared. That should make sense. Putting the mu inside the sum. Mu times n, if we, or negative mu times n, if we just put in a mu here. But because there's also this 1 over n here, the summing and the 1 over n would cancel out. So in this case, we have 1 over n sum of I equals 1 through n of xi minus mu, and the whole thing is squared. Not the whole thing, because everything within the expectation is squared. Right, so we couldn't normally just take a thing outside of a sum and put it into a sum. That would be akin to multiplying this by n, because we're summing it by itself n times. But this is not just a sum, it's an average. So this mu is getting affected by, it's essentially getting multiplied by n, and also is getting multiplied by 1 over n, and so those cancel out. And this allows us to put these inside the same brackets, which is pretty convenient. So the next thing that we're going to do is we're going to distribute this squaring. So we're going to have 1 over n squared, which is equal to 1 over n squared. 1 over n squared is equal to 1 over n squared. Because 1 times 1 is 1, and n times n is n squared. And this is times this sum I to 1 and xi minus mu squared. In fact, we can even pull the, because 1 over n is a constant, we can even pull it out of the expected value. Is that true? Yeah, because 1 over, so we can do this later, we can do this now. We're going to, an expected value is just an integral. We can pull out 1 over n squared. And so now we have the expected value of the sum of xi minus mu squared. Okay, so now here's where we get some action. Now I want to define. Yeah, all right. So the next part I think is maybe the trickiest part of this proof, where we are going to have 1 over n squared times the expected value of this thing squared. So that's equal to the sum of xi minus mu times the sum of xi minus mu. It's actually sort of proper to write this as xj, just to show that we're indexing separately, even though these are the same. They're sort of like different for loops, or different while loops, I guess. Since you terminate when either I or j, when I gets to I is equal to n, then you terminate, and when j is equal to n, you terminate. All right, so here, so this is actually kind of tricky. We're going to, so note that this is a, this is like a long, this is a pretty long term. This is like x1. So this is equal to, the sum of I equals 1 to n of xi minus mu is equal to x1 minus mu plus x2 minus mu plus x3 minus mu, all the way to plus xn minus mu. And we're going to multiply this by itself, squared. So there's a question of how to do this. This sort of seems like a lot of stuff to multiply. So the first thing is I'm just going to simplify by instead of talking in terms of x's, we're going to talk in terms of y. And yi is equal to xi minus mu. And so the thing that we're doing with this translation is we are sort of moving all of our data points over. We are shifting so that right, each of these is a deviation. Each of these is a deviation, right? So this is a particular data point. This is a particular data point, and then this is the population mean, and what's the difference between them? And so the expected value of each of these terms is equal to 0, because the expected value of x of any given x of xi is equal to mu. And this is just it. What am I talking about? Well, we're just going to substitute for this. This is easier to manage. And so what this means is, instead of this, we have the sum of n, sum 2n from I equals 1 to n of yi, which equals oh yeah, this is misleading. We're going to square this, which is equal to y1 plus y2 plus y3, so on till we get to yn. And again, this is a thing that we're going to square. So we want all of this we want to square. So how do we do that? Well, basically what that means is we're going to take each and every one of these y terms and we're going to multiply it by the whole expression. So if we take the first one, this is equal to, it's sort of going to be equal to an n by n matrix. So we have y1 squared, because we have y1 times y1 plus y1 times y2 plus y1 times y3, and so on until we get y1 times yn. So that's one thing. That's like the first column. This first row is we are multiplying y1 by every other term in this expression, and then we're going to add that to a second row, which is equal to y2 2 times y1 plus y2 squared plus y2 times y3, and so on until we get y2 times yn. And so one thing that you'll notice here is there's sort of a pattern. We have like an n by n series of terms that are all going to be added together, right? Everything here gets added to everything here, and n this way, again, n columns and n rows, and there's sort of that. Mostly, we have two separate terms that are going to be added together, right? Y1 and Y2. Excuse me, not added together, multiplied together, but also we have this diagonal. And the diagonal has squared terms, so also y3 squared and y4 squared. So we're going to treat those two things differently. So if we want to know what all of this squared is, it's actually two different sums. First, it's the sum of all of these squared terms. That's one component. So what we get is equal to the sum from I to I1 to In of yi squared, right? y1 squared, y2 squared, y3 squared, y4 squared, all the way down to yn squared. So that's the first part. And then we also have all of these other places where there's unlike terms that are being multiplied. So that is also a sum. The sum, but it's a little bit more complicated. It's the sum of I equals 1. Excuse me, I equals 1 to n. And I'm not sure what the best notation for this is. And another, we have two variables. Just to keep, we have two variables. We have I equals 1 and we have j equals 1, both going to n. J equals n, I equals n. And importantly, j does not equal I. And j does not equal I because any point where j equals I is a place where it would be squared. And in that case, it's already captured in this first term. And we have yi times yj. So this is sort of thought of as it's like a loop within a loop. So we're going to take every, the code would be something like for xi in xi to xn, and for xj in xj to x1 j to xn if xi not equal to xj. No, that's not true. If I is not equal to j, if j is not equal to I, then xi times xj. Yeah, which gets added to equals new sum plus equals new. Something like that. So we're looping through all of the i's, and we're looping through all of the j's, and every time I is not equal to j, we're multiplying I by j, and that's covering the whole rest of these. All right. So now we want to simplify that. So one thing that we're going to do is remember that y is just a shorthand for yi is just a shorthand for xi minus mu. So we're going to put those back in. And I equals 1. Equals xi minus mu squared. Actually, is this a good time to put them back in? Plus sigma n I equals 1, j equals 1, I not equal to j, I times j. All right, and then we're going to treat these two. So now we want to simplify these, and I'm out of board space. I'm just gonna use it up over here. So we're gonna treat these two things as pretty different. We need to simplify them separately. So the first thing, which makes sense to do first. So the first thing is I'm not going to give a rigorous proof of this, because doing a rigorous proof of this requires some math that I don't have yet. But we can notice that, oh, this is not what I wanted to write. Is equal to xi minus mu times xj minus mu. So the first thing is about this section is we notice that these xi and xj are just different independent draws from I'll be back in one moment.